Hey Professor, this is Rob Hines, and this is my video solution for our Project 2 design project. Okay, so for Project 2, this project is titled Optimal Rocket Ascent Under Gravity and Drag Using MATLAB, and this is our design project for this semester. So basically, for this portion of the video, what I'm going to do is I'm just going to go over the general criteria, constraints, given values, formulas, and whatnot, just so we have an idea of what the project is and how we are to go about the design project, the design process. So for the objective of the project was to model and optimize the ascent trajectory of a hobby rocket to achieve maximum altitude. Basically, we just use MATLAB to simulate the rocket's dynamics because we're not actually making a hobby rocket, but we're just simulating everything in MATLAB. And we want to simulate it under the influence of general constraints like gravity and drag, and we also want to consider the variation in mass due to fuel consumption, because the mass will decrease as the fuel burns out. The goal of this design project is to find the optimal thrust profile that maximizes the rocket's altitude. So you have the problem statement. This is the exact same as the objective, more or less. I'm not going to go and reread all of that. For the system dynamics, the rocket's motion is governed by the following differential equations, considering the effects of gravity, drag, and various mass. So for our system dynamics, we have three different equations. As you can see here, we've got number one, our rocket dynamics, number two, our mass variation, and number three, our altitude. For number one, our rocket dynamics, we have this formula here, as you can see. I'll zoom in a little bit. And as far as all the variables are concerned, V represents the velocity of the rocket. T, lowercase, represents time. Lowercase m is the mass of the rocket at time t again, and it decreases as fuel is burned. Capital T is our thrust, and it's provided by the rocket engine at time t. Capital D is the drag force, and it's modeled using this equation here. And then that equation, CD, capital C subscript D is the drag coefficient, P is air density, and A is the cross-sectional area of the rocket. G is acceleration, and we know the acceleration of gravity is 9.81 meters per second squared. And that concludes the first equation for our system dynamics. Second equation for our system dynamics is our mass variation formula right here. And the key things that we want to take away from this formula is that ISP is the specific impulse of the rocket's engine, and the unit of time measurement in here is seconds. And then G is the standard gravitational acceleration, once again 9.81 meters per second squared. That's constant, that never changes. And then 3, we have our altitude. This is the formula for our altitude. Okay, in addition to our system dynamics equations, we have our initial conditions as well as our given data. So our initial mass, MO, is 1.5 kilograms. This includes fuel and the structure of the hobby rocket. We have our initial velocity, V0, at, obviously the rocket starts on the ground at rest from 0 meters per second. Then we have the initial altitude, once again 0 as it starts from the ground. Then we have the dry mass of the actual hobby rocket. This is the mass of the rocket without fuel inserted. That's 1 kilogram. Then we have the maximum thrust, Tmax here, it's 40 newtons. Then we have our specific impulse, this is 100 seconds. And we have our drag coefficient as we covered up here, CD, and that is 0.75. Then we have our air density, P, and that is 1.225 kilograms per meter cubed. And then we have our rocket cross-sectional area, and our area is 0.01 meters squared. Okay, so in addition to all of that information, we have our actual tasks. These are our actual prompts that we want to solve in our project. So first we want to model the rocket dynamics, we just do this portion utilizing MATLAB. And we want to interpret our results. This is part 2, utilizing MATLAB, of course, again, simulating it. And then 3, we have our optimization piece, once again, solving in MATLAB. And then these are just the general submission requirements, assessment criteria, submission format, etc. All right, now that we've got all of that stuff out of the way, we have all of the code that we did in MATLAB for this project right here. And I'm going to go through and explain each bit of code in detail. And I will try to highlight the portions that we're going over as well. Obviously, this part right here, we use the CLC and clear, close all functions just to close everything out, start fresh. And then we highlighted, or we classify parts 1, 2, and 3 and what the objectives of each part are. So for part 1, you have lines 2 and 3. Basically what these lines are doing is they're setting up the thrust values and they're initializing the result array. Then we have lines 5 through 8 here. I like these. These lines right here, basically for each of the thrust levels, what we're doing is we're simulating the rocket using the ODE45 function with that respective constant thrust. And then we're also recording the final height from the output trajectory. And this is just general code for clarifying and classifying and for formatting. That leads us into part 2. As you can see, line 2 here, we have our thrust, and we just decided to choose an initial value of 3,000 for this analysis. We have line 3. What line 3 does is it basically just simulates the rocket's dynamics using, once again, the ODE45 function. These 3 lines right here, these are just the altitude, velocity, and mass, and we're basically extracting this from the ODE solution, more or less. Okay. This section right here, basically what that section does is it plots the mass over time, and it just makes sure that it doesn't drop below the dry mass. Okay. Basically, line 16 and 17, these are just plotting the altitude, and it calculates the maximum weight, or maximum height, excuse me. Then we have lines 19 and 20. These find when the rocket switches from ascent to descent, when it reaches that top point in the air and starts to drop. The velocity will change signs to identifying that it's losing altitude instead of gaining altitude. And then we have this section right here, or lines 23 and 24, excuse me. Basically what these do is they find when the altitude crosses 0 again, and that is basically when the rocket lands or crashes, or however you would want to identify or describe that action. Okay, so that's the long and short of part 2. Then we have part 3 here. And we have this section right here. Basically what this does is it just defines the time horizon and our initial guess for thrust. Line 5 here, this specifies the thrust constraints, and it does that from 0 to 5,000, as you can see here. Kind of ran out of room a little bit here, but line 8 basically minimizes the negative altitude, and it also maximizes the altitude using the fmin con function. This line, is this the right line? Yes, this is, okay. Line 9, basically what this does is it runs a simulation, and in running the simulation it uses the optimized thrust vector, and then we have lines, the section here, and it basically just plots the resulting optimal thrust profile over a specific period of time. then this whole section right here, basically all this is doing is it integrates the Rocket ODE, and it uses a piecewise constant thrust profile. So those are all of the parts of the code for the project. In addition to just explaining the code, I'm also going to explain how the code actually meets, the project requirements that the problem statement suggested. So what the problem wanted us to do is it wanted us to simulate constant thrust scenarios. In part 1, it simulates from 1,000 to 5,000 newtons, and it plots the final altitude. In addition to simulating the constant thrust scenarios, the project also wanted us to plot and analyze our results. Part 2 gives us plots for mass, altitude, and velocity, and it also extracts key values. The design project also wanted us to make sure that the mass never falls below the dry mass. Once again, in part 2, this is verified using a mass versus time plot. Then the project wanted us to find our max altitude, ascent, and flat time. All of these values were calculated from part 2. See if I can find the exact specific, using these lines here. Then the design project wanted us to maximize altitude using variable thrust. Part 3 uses a specific function to optimize the thrust profile under the thrust constraints. And then lastly, what the design project wanted us to do is it wanted us to present optimal thrust profile, and we plotted that in part 3. So yeah, that is the long and short of this design project.